Welcome to all those who are interested in learning the concept and understanding structural engineering completely. Because I already told in the earlier class, this is class number lecture 41 of part 3, is what actually is moment of inertia. As I told earlier, see, moment of inertia everybody knows. Sometime if I ask moment of inertia, some will tell BDQ by 12. I will ask them, I did not tell rectangle. What answer you are giving? I asked you what is moment of inertia. You don't give me expression for moment of inertia. Sir, that's what we know. Some people will tell I. They will tell, some people will tell I. I is the symbol. It is not meaning of moment of inertia. What is BMD means? Some will tell, sir, bending moment diagram. No. If I ask what is BMD means, define bending moment diagram. Same way. See, what actually is moment of inertia? Question mark. Note, our discussion is for area moment of inertia, that is second moment of the area about an axis. Okay, now, in this class, you will get complete knowledge. Not only knowledge, understanding. To the mind, a feeling will come when you next time onwards. A feeling will come. See, I will write here at the end of the class. See, I will write here later. At the end of the class. Later I will write what is this one. You will get the feeling and you will understand. See, like I told, when I see a beam, I can see moment of inertia. Actually, I cannot see. How I can see it? But what happens is, it is visible or I can understand to the inner mind. Like happiness or sorrow, pain. See, you cannot see the pain, but you can feel it. So I will see that you understand each and everything. You will get complete knowledge only if you go through entire class with dedication, most important, and of course with full patience. Lot of patience required. Once in a lifetime, these things, those who are serious, should go through. Each and everything I tell here, some of them I will dictate here. You should write it. Some of them I will write in the board or some explanation I will give. I cannot write each and everything. That all you are right. And also note, when I go to moment of inertia, I cannot go to moment of inertia, the real meaning of moment of inertia, unless I reach some. In strength of materials, there is a chapter called bending stresses. That bending means flexure and slope and deflection, that is flexural deformation, and also torsion. Unless I go there, I cannot tell why the term it is called moment of inertia. See, I already told you last time, sigma dA y square. Okay, that engineering mechanics point of view, okay. See, last class is for general. They continue next class. They don't bother why it is that way, but to understand what actually moment of inertia, I have to go to strength of materials, bending stress or flexural stress, slope and deflection, torsion. And remember, what all required, I will write in the board briefly. You should believe me. I cannot, because everything I tell you, some I will tell, see the strain, stress, etc. You believe me. It will come systematically in strength of materials. So, later, when I go to strength of materials, I will tell, see, when I derive the basic bending theory, I will write term there, sigma dA y square. Then I will tell, see, remember, sigma dA y square is moment of inertia. Now go back to that class. Which class? Understanding class of moment of inertia. That is what actually is moment of inertia. Go back and study and come back. Same thing for slope and deflection and torsion. So, here, but one thing, majority, almost more than 95% of the people who are using my class, they already finished BE or the engineering they are finished or they are already in the practical field. Therefore, they will be knowing it. If I tell m by I equal to sigma by y equal to E by R or slope and deflection, if I tell WL cube by 24 EI for UDL for simple support beam, 5 by 384 WL power 4 by EI, T by IP equal to tau by R equal to G theta by L, They will tell, yes sir, we know it. But very sorry, you don't tell you know it. I will tell in the class. You tell you heard of it. Know it means danger. When you tell we know it, you should know correctly what is each and everything. Then they will tell, yes sir, we heard of it. Okay, leave it now. Now, lastly, at the end of the class, or by the time you reach the end of the class, if you show full dedication and full patience, I will guarantee you can tell with confidence and pride that I know what is moment of inertia. Now you can tell, yes, when you tell moment of inertia, I can understand what is that one. What is the real meaning of moment of inertia? What is its important? And for that matter, remember, structural engineering knowledge is incomplete without knowing the real meaning of moment of inertia. Okay, I'll remove this one now. I'll start one by one now. Now, before I enter into the real concept of moment of inertia, remember, this class will be a lengthy class. It will take more than 2 hours. Surely more than 2 hours, I think. Okay. I will just give a recap for you. Recap. See, already, actually recap. Okay. Recap. Already over in lecture 40, previous lecture. Lecture 40. But I should write it because reason is there. Previous lecture. Consider an area A. Class, those who are commenting, I told already we won't waste time now onwards. Every class telling area, lamina or cross sectional. So in future now, if I tell area, I may tell rectangle, triangle because they have got areas. So area class, that is lamina or a plane area, or to be perfect in structural engineering, it is a cross section of a structural member. Okay, sufficient. I won't waste time now. Consider an area A as shown. See, total area is A. Now, consider elemental area dA at y from dA. Elemental area dA. Let y be perpendicular distance from dA to an axis, any axis, say AB, class. I am writing AB because today I am discussing moment of inertia about a random axis, say AB. Later, the most important is centroidal axis. That will come later. Right today now, we don't know about centroidal axis now. So an axis AB, to understand AB class, it can be centroidal axis. Now, moment of elemental area dA about AB axis, moment of the elemental area dA about AB is area into distance dA into y. Okay. Note, this is called first moment of the elemental area dA about AB. One small note you make here. See here, note. In centroid, earlier, we continued by telling, therefore, moment of the entire area about AB equal to sigma dAy or sigma integration of dA into y. This we told in centroid. Then we wrote what? That sigma dAy divided by area will give y bar. If I take sigma dAx divided by area, you get x bar. That all told earlier. So this only reminder for you. See, in centroid, we considered this is for elemental area. We consider full area, but not now. Now not required. Now, see, this is moment of elemental area dA about AB. Now, therefore, second moment of the elemental area. Once again take moment. Area dA about AB is dA into y is the moment of the area. So whatever moment you got, once again take moment into once again y. See, into once again y. Once again y. Or some places they will tell moment of moment. See, moment is dA into y. Moment of moment, dA into y, but actually I don't like this word. I don't like the word moment of moment. Looks very odd for me. So better is second moment of the elemental area dA about AB is dA into y, which is called moment of inertia. Our symbol, see, Right here. In our class, moment of inertia, our symbol is I with the suffix. With the suffix. The suffix is always axis. Remember, I won't tell again and again now. So, dA into I, that is called, which is called moment of inertia I of elemental area about AB. That is IAB for elemental area dA. Somebody will tell immediately, sir, why? Sir, you told this class is meant to understand why, and you are telling which is called moment of inertia why. Wait, if I can tell the answer right now only, then I would have told in the previous class only. Lot of discussion required. This is not something which you can tell why it is called moment of inertia. I will tell you later. So right now, which is called moment of inertia. Okay. Therefore, moment of inertia of which one? Elemental area dA about AB, see, about AB. I will tell now second moment of inertia, or you can tell if you want second moment of the area. Okay. Second moment of the area. Both are same. Area. Elemental area dA about AB equal to how much? This is for elemental area. What I told, it is dA, that is symbol. See, symbol is, that is I about AB, but remember, this is not I about for entire area. I should extend further. I about AB for only what? For elemental area. For elemental area dA. See, so much I am explaining. Elemental area dA equal to sigma of, see, sorry, first I don't write sigma. It is what I got, dA into y is dA into y square. That is product of elemental area, see, very important term, elemental area, and square of perpendicular distance from elemental area to axis AB, to the axis, to axis considered, that is AB. This is I for elemental area. Therefore, I write here moment of inertia, little later MI, that's all. Moment of inertia of entire area about AB, that is called this time simply IAB. No, see, here it is for elemental area, no elemental area. Now IAB equal to, see, sigma of dA into y square. This is basic concept, or further better is, or it is actually technically integration of dA into y square. This is what you are using later, either sigma dA y square or integration of dA into y square. This is I for AB. Now, 1 minute, something I want to explain now. So, now this concept I explained, right? Now, therefore, the basic concept of moment of inertia is, still I have not told you why it is called moment of inertia. That comes later. To get moment of inertia of an area about any axis, divide the given area into infinite number of elemental areas. Infinite number of elemental area. How many? 10? No. 100? No. 1000? No. 1 lakh? No. 1 crore? No. Full dot, 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 dot. Then find, see, sum. Remember, sum and integration both are same. And find sum of, see, sum of product here. Okay, I'll do one thing now. I'll make it more clear now. This one is the product required here. So I write to make it more clear. Okay, just to make more clear. That is IAB equal to sigma is black color, sigma is not sigma of that elemental area, dA into y square product. Find the sum of product of each elemental area and perpendicular distance from that elemental area to the axis about which moment of inertia is required. Or, see what I am doing now. You write now. He wrote the statement, then he removed everything, right? Removed everything, and he put a demo. You tell, he put a demo. See now, demo. He took, right, my name. He considered an area randomly. Then he considered some axis AB anywhere randomly. Okay, now start. See, some small elemental area here, dA, right here. One elemental area he marked, very, very small area, multiplied by square of this distance plus one more elemental area here into square of this distance, one more elemental area here into square of this distance, one more elemental area here into square of this distance, another elemental area here into square of this distance, another area into this distance square, another area into this distance square. So that then she filled up the entire area with the infinite part of small, see, dot elemental area. See? Okay, then you write, yes, you understood. See, this area into this distance square, this area into this distance square, this area into this distance square, one more area. You go through this class. That way you have to do it. That is the principle of moment of inertia. Okay, now I will go to next part. Next part is where you will understand and little later get the feeling of moment of inertia. That is next part. Now time has come to understand moment of inertia. But there is one problem. See, you have to enter strength of materials. Still the course is not started. It will start after my moment of inertia is over, then friction I will cover, then I will enter strength of materials. So, what all I tell now, you need not bother. But many of you already know it. See, bending stresses, or bending is also called as flexure, and a little later flexural deformation or deformation due to bending, that is slope and deflection. Little later, if time permits, I will go to torsion. Actually not required, because once I explain here, it will be same concept there also. Okay, now what I will do at that time is, when I start strength of materials, when I reach this stage, see, first I will do simple stress and strains, principal stresses, compound stresses, shearing force and bending moment. Then I will come to bending stresses, and then later shear stresses. After that one, deflection, slope and deflection. Now, I will consider pure bending case. Sorry, that's all, nothing further. I will apply a couple mm here. Supports also not required. Some member here. Then I will tell you consider a very, 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 very small elemental length here. See, some length, but exaggerated. See, exaggerated. Due to this bending moment, beam will bend like this. You never bother now. See, beam will bend like this. Okay. So then I will tell you upper side will be in compression, lower side will be in tension. That all I will explain at that time. Then I will show the deformation here. There is one level here where it is E dash, see, red color. That is called neutral layer or neutral plane or neutral surface. It is not neutral axis. So many people, they make a mistake. They tell this as neutral axis. No, it is not neutral axis. Neutral axis comes in the cross section. Okay, later I will tell. Now, let it bend in the form of an arc of a circle. See, center is O. Then I will write here, let the angle be d theta here. This angle d theta. Then I will tell, see, now you don't bother, let sigma be bending stress at distance y from neutral layer. Oh, neutral layer is red color. Okay, neutral layer. Okay, not required. Neutral layer. Right now, neutral layer. Later, neutral axis, neutral layer. Then I will tell so many things. I won't explain for you. I will tell something. Initial length is dx. That is also equal to here, equal to r d theta. I will consider GF, see, y is, that is at GF level, some distance at y from here. Then I will tell for this GH, initial length is r d theta, the final length I will tell r minus y into d theta. Then I will tell, therefore, change in length equal to r d theta minus of r minus y d theta or equal to y d theta. Their change in length. Therefore, I will tell strain epsilon equal to y d theta is the changing length divided by original length is r d theta. D theta cancels, or you will get strain at that level is y by r. Then I will tell, let sigma be the stress. We know that stress sigma equal to strain into Young's modulus. Then I will tell, therefore, the stress sigma equal to y by r into E. Then I will tell, therefore, or I will tell sigma equal to E by r into y. I will write one more statement there. Or I write sigma equal to, so E is black, okay, E is black, y is green, variable, okay, y by r into, or I will write sigma equal to E by r into y. Then I will tell, see, therefore, y power 1, linear variation, so many things I will tell at that time. Then I will write, therefore, see, sigma by y equal to E by r. I will write the statement there. I will call this as equation 1. Today you don't bother because your purpose is coming little later. If you know it, no problem. This is not the time derivation. You imagine I am talking to myself only. Then I will consider the cross section. Any cross section, but one thing is there, it should be symmetrical about y axis. That's required. So I show something like this cross section. Then I will tell, in the cross section, you can see an axis here pass into centroid. See, in the cross, this is a cross section, pass into centroid. I will tell that is called neutral axis, pass into centroid. Then that GH level, I will consider at this level an elemental area dA at y from here. Then I will tell at dA level, see, for elemental level dA, stress sigma equal to, already I got, see, sigma equal to E by R into Y. I will write E by R into Y. Into Y, okay. Into Y. Then I will tell, see, when the bending moment is this way, it will compress here. So a resisting force will come. A resisting force dF will come equal to stress sigma into dA or equal to E by R into Y into dA is the force. Then I will tell moment of that resisting force about neutral axis equal to the force is E by R, black will do no problem, E by R into Y into dA is the force multiplied by distance Y or equal to E by R into dA, oh see, dA Y square. Then I will further tell this is moment of the resisting force in the elemental area. There are infinite number of elemental areas here. So I will tell algebraic sum of moments of all such resisting forces, which is actually is the internal resisting moment or internal resisting couple developed by the cross section, which is responsible to resist the bending moment M. So that will be equal to M. So that M equal to sigma of E by R into dA into Y square. I will write this way. Okay, now do one thing. Do not bother anything about it. See, I already told you. These all we will get in the bending stress chapter. Okay, I remember now. I just told derivation. See, derivation for me, I don't have to by heart. Or, see, dA R square. Now I will tell one thing. Now, then I will tell after this one. Now, we know that, see, at that time we will write we know that sigma of dA into Y square is, I will write what? I will write is second moment of the area at that time, because why we are covering now. I will write at that time is second moment of the area, of entire cross section about neutral axis, or it is also called as moment of inertia of cross section about neutral axis, or say I about NA. I will write at that time. I will write INA at that time. Then I will write, therefore, see, M equal to, see there, therefore, I will continue there, M equal to sigma E by R is I neutral axis into E by R, or R when prediction, some other way, see, or E by R is constant, E by R into sigma dA Y square is, actually one more thing I will write here, equal to E by R outside into sigma of dA Y square. So it is E by R into I about neutral axis. Then I will tell, therefore, M by I means I about neutral axis, equal to E by R. I will call this as equation number 2. Equation 1, equation 2. Then I will tell from 1 and 2, we can tell, see, M by I equal E by R, E by R is also equal to sigma Y by. So I will write then the basic equation, right? The basic bending equation is bending or flexural bending equation is M divided by only I, sufficient. Understood. When you write there, you don't write I and me. I understood. It is I about neutral axis. M by I, see, M by I equal to, I write sigma by Y equal to E by R. This is a proof for the bending equation. I will write at that time. Now I will go for some discussion. Okay, this I will write. Okay, then further. Some more thing I'll tell. Now only. See, what all I told now, you never bother. You just agree. That's all. Just agree with me. You tell that yourself, no, he will tell later, no problem. But then why you are telling now? I am telling now because without this I can't explain moment of inertia. Without this I cannot explain moment of inertia. Okay, now I will tell something else. We can use this equation two ways. One is m by I equal to sigma by y, or see this way, you can use this way, or you can use this way, or m by I equal to E by R. This is how you use it. Now, this is for stresses, bending stresses, okay. This is for bending stresses. Bending stresses. This is for flexural deformation. Flexure, I can tell about R, radius of curvature, that all I will tell you at that time. No time now, because now time purpose is to understand moment of inertia. Flexural deformation, that is slope and deflection. Slope and deflection. Slope symbol is theta, deflection is delta, flexural bending stress is sigma. Some people use F also. I will tell all these. Then I will write there. No, not there. That's all. See, in the bending stress chapter. But now I will tell, now, see, very important. Now, suppose we are not able to understand the real concept of moment of inertia, then instead of I, we would have written sigma of dA into y square. Sigma of dA into y square. Then our equation, bending equation would have been, the bending equation would have been m by sigma dA y square, color I will put later, equal to sigma by y. It would have been like this. Suppose we are not able to decide sigma dA y square, what is that one, how to simplify it. Suppose you are not able to understand that one, then see, and other will be m by sigma dA y square equal to E by R. We would have written this way. This is for stresses, for stress calculation. This is for slope and deflection. Okay. Slope and deflection, to make more clear now. Deformation, slope and deflection later. We would have written like this. Then what will happen? See here. What will happen is, see correctly now. 1 minute, I have to put the ink for the pen. So little pause required. Little ink required for the pen. It is writing little dull. The most powerful term is coming now. Now is the time. I don't know whether I told this or not. If I have not told, see, now, suppose we are not able to understand the real concept of moment of inertia. Suppose, imagine, the real concept is not known. Sigma, that is sigma dA y square. See, remember now, it is a green color actually. Sigma dA y square is a green color because it is for everywhere. I put green color because why? It is summation for entire cross section, sigma dA y square. Okay. Then, suppose you are not able to understand moment of inertia and no one told sigma dA y square what to do. Finally, somebody got the idea. So before that, see, now I am telling how the term moment of inertia came. Then, for bending stresses, we would have written m by sigma dA y square equal to sigma by y for bending stresses. For, I told stress means bending stress only for bending stresses. not required right everywhere. One place sufficient, bending stresses. And for flexural deformation, right here, for flexural deformation, you would have written m by, not I, m by sigma dA y square equal to E by R. What is E, what is R, I will not tell here. Young's modulus, radius of curvature of neutral axis, 1 by R is called curvature. That all I will not explain here. It will come later in slope and deflection. This is what we have done. Now see, that is, I will write once again now. Then, see, same then once again. If you consider right here, then consider cross section. Consider cross section. Centroid is here, neutral axis here. This all will come later. Everything comes later. You take an element at y from neutral axis. This is black color, not green color. Y, fixed distance. Y is a fixed distance, some fixed distance. Somewhere you want to stress y. Then instead of writing sigma at y from neutral axis, usually what happens, see, your equation is m by I equal to sigma by y. So sigma equal to m by I into y. Instead of writing sigma at y from neutral axis equal to m by I into y, we would have written sigma bending stress developed, see here, bending stress developed at y from neutral axis due to bending moment m for cross section. Again I am telling cross section equal to m. That is bending moment for cross section by not I, sigma dAc. This y is a particular point. This is not y. Infinite parts are there. M by sigma dA y square into y. Then write everything. Okay. We would have written in that way. Now see here, 1 minute, don't come here now. This is what we would have written. Okay. Now, one more thing is there. I will tell now only. Okay, this I will remove now. See. I won't waste time telling derivations on. See, somewhere you tell, please wait. Please wait for some time. Right? You tell wait. Actually do one thing. You write before coming here only write here. Consider m by I equal to E by R. This is used for flexural, used for flexural deformation. That is usually slope and deflection. I am making the concept clear for you. Slope symbol is theta, deflection say delta right now. Later y I will take. Okay, now instead of this equation, then right here, take an example, one simple example. This I will remove now. Consider a simply supported beam of span L subjected to UDL of W per unit length. I never put kilonewton per meter, unit length over entire span. That is like this. See, I'll put somewhere here. Okay. This I can remove. Okay, this I can remove. I touch here. See, this is the beam, simply supported beam of span L subjected to UDL of intensity W per unit length. See, I never put W kilonewton per meter. Now, this beam, the initial position is here. What will happen? See, this beam, when you apply this loading, will bend like this. This way it will bend. See, this is called flexural deformation. Now, in the center, there will be maximum deflection. For this case, delta max. And support will be maximum slope, theta max. This is theta max, this is also theta max, both are equal. This is theta max. Then, okay, now This is already over. Your theta max will be W into L power 4, WL cube by, I don't know, 24 EI. Y means I know it, EI. And your delta maximum is 5 by 384 WL power 4 by EI is the expression we are going to get right here. This we will get when you, in the strength of materials, when we consider slope and deflection for the beam. Today you believe me, okay. To be believed right here. Today we will believe, sir. You write there. What he tells we will believe. I told for that matter everything you have to believe. Okay, now I will add one more thing now. See, same way, now I will add here. See, leave it now. I will remove this one now. I will put here. Also, and also for flexural deformation, that is for slope and deflection, suppose it is a simply supported beam of span L subjected to UDL of W per unit length. See, everything I am writing W length. Then initial position, the beam will bend like this. This is too much actually. See, this is your, I write here. Okay, I write this. No. To make more clear, I write somewhere there. Okay. This is maximum center actually. This is red color I will use. Red required. No, red, not red, black only. No red color. Okay. This is your delta max, maximum deflection. This is your theta max. Space is not there, not tangent here. This is also theta max. Then means same thing. Suppose, I told you, suppose you have to write, if you write here, if we do not understand the meaning of sigma dA y square, we would have written, see, we would have written maximum deflection, or maximum slope first, okay, maximum slope, that is theta max is WL cube by 24 into, see, I will do one thing now, I will put E here, E into, suppose you don't, see, I told you, if you don't understand the meaning of inertia, then we would have written E into not I, sigma dA y square. Sigma dA means entire cross section, and we would have written maximum deflection, delta max. This is for understanding purpose. Actually it is 5 by 384. That is not important for you. WL power 4 by E into sigma of dA into y square. That is what you would have written. See, now you write here this much. Now write everything I dictate or explain now. Now I am going to explain or dictate. Everything you are right. If you don't write, you are losing. See, start. Once again recap now. Right here, this is the, we would have used this expression to find stress at any distance, at a fixed distance. Y is fixed, some distance y. It is not variable now. But sigma dA y square is variable. At one particular point at y from neutral axis, if you want bending stress developed, see, when you apply bending moment, stresses will come. How much stress developed? Anywhere at maximum will come at the extreme fiber, that will worry later, not now. How much stress will come? M by sigma dA y square into y. And If it is simply support, this is for bending stresses. And if you go to flexural deformation, that is m by I equal to E by R, instead of m by I equal to E by R, we would have used m by sigma dA y square equal to E by R. Then for this beam, we would have written maximum slope this much, maximum deflection this much. Now, one question from my side. Now, right, start. One question from my side, from me. You have to correctly think and answer. Bending stress developed. Black color highlight. Usual black color. Bending stress developed or flexural stress. Bending stress developed. That is sigma, slope, theta, and deflection, delta. Are these all good or bad? Good or bad? See, slowly I will tell now. That's why I told you need infinite patience to my class, this class. Good or bad? Stresses developed one by one. See, everything I'm dictating now, stresses coming. Good or bad? 100%. All are bad. All are bad. Very bad. Very, very bad. Very, very bad. Reason why? In the class I will ask, see, you want to, in a building, your own beam, do you want the stress to be more or lesser? Sir, lesser, sir. Why? Sir, more stress is problematic, sir. Yes, correct. Do you want the beam to rotate this way? No, sir. How we can stay in the building? Or do you want the beam to deflect like this? Sir, we will run away from the building. If you see a beam where it rotates this way, see at the support, see heavy slope rotation and heavy deflection. Today beam is this way. When you come to the building tomorrow, you see the beam like this. What you will do? You will vacate the building and run away from there. See, slope and deflection you can see. Stress you cannot see. It will be calculated. Stresses you cannot see. It should be calculated. Okay, now. So, stresses developed or slope and deflection, all of them are bad. Or common sense. See, common sense I will tell. People will tell sometimes, why are you looking so dull? I've got a lot of stresses. See, he is not telling these stresses. He is telling internal stresses. See, stresses. I'm fully stressed. Oh, I don't know what is happening now. So much of pressure. See, so much pressure on me, financial pressure or work pressure or traffic going early pressure or so many pressure and stress both are somewhat same. Pressure. See, I am fully pressurized. I don't know how to manage all this one. Financial problem, financial stresses or pressure. See, fully stressed. See, fully stressed. Suppose someone will take your finger and keep on pressing this way. You will tell. Stresses are bad. Remember, stresses are bad. So I tell you here, stress is bad. Bad. Slope also is bad. Bad. Delta also bad. Somebody may tell, what is bad and good? I will tell you, keep quiet. If someone will comment, you are using some words which are not correct for structure engineering, I will tell, get out from my class. That's all. I am trying to explain everything to people to get the feeling of moment of inertia. That's why you require. If I talk technically, you won't understand. They are bad. See, I told, stress is bad. Fully stressed. See the facial expression. Too much of pressure on me. Stress. Slope and deflection, deformation, good. See, suppose someone will twist your hand this way. He will leave it. Suppose because of the twisting, if a strain comes there and bone gets cracked, see, deformation, good or bad? Sir, bad, sir. So, deformation is bad. So, every structure you are happy if stress is lesser and slope and deflection also is lesser. So, lesser stress. See the face here. See, now pressure. See what you will tell. Now my problem is solved. Now I am having very lesser stress. See, no pressure nowadays. Nowadays I am feeling confident. I am okay. No pressure or stress. Deformation. No. Now our beam is okay. Something is done. Now I can't see the beam bending. See, yesterday the beam which was dangerously bending this way. Now you tell no. Some remedy is done. Something he has done. Some support. Something he did. You don't bother. Or maybe he replaced the beam. He replaced the beam. See, the new beam has come. Now see, the beam is good. It is not bending. Therefore, bending stress and deflection. See, this is the stress part. This is deformation part. That's what I want to tell. The stress developed and deformations, they are very, very bad. So, they should be controlled. See, I told they should be controlled. Controlled means when you design a beam, you should see that the stress will come lesser and also deformation will also come lesser. That is happy news. A beam, lesser stress and lesser deformation are good. Okay, now slowly we will go for it now. We are about to get the feeling of moment of inertia now. See, now is the time to get the feeling of moment of inertia. I told all are bad. One question. Okay, now. See now, sigma dA y square comes in denominator. Sigma dA y square comes in denominator. Sigma dA y square comes in denominator. Therefore, in all the therefore, for stress and also slope and deflection, the term sigma dA into y square comes in denominator. That means, see here, that means what? I am dictating now. See, I am dictating. You should write. That means you should write higher is the value. See, that means higher value of sigma dA y square means very, very good. Y is very, very good. Higher is sigma dA square is very, very good because stress, slope and deflection all will decrease. All will decrease. Whereas you write lesser is the value of sigma dA y square is very, very bad. Why? If sigma dA y square is lesser, the stress will increase, slope will increase, deflection will increase. Ayo, we don't want it. See, see, so much of stress, so much of slope, so much of deflection. I am not staying in the building. See, therefore, vice versa, you write it. Now, the important term, moment of inertia. Why that term came? See, comes in denominator. Now, see. I told you I will give a feeling of moment of inertia. 1 minute now. I will pause the recording because some recording is already. Sometimes it won't record if I don't pause in between. Okay, now I will tell you why it is called moment of inertia. See, I already told you sigma dA y square comes in denominator. Therefore, higher and higher is sigma dA y square. Higher and higher sigma dA y square means lesser stress, comma, and lesser deformation. lesser deformation. Lesser deformation, that is slope and deflection. Slope and deflection, lesser deformation. Or, therefore, see here, I told in denominator. So, what this denominator will give you? See here, WL cube all fixed. Bending moment is fixed for a given bending moment. Y is also fixed, but sigma dA y square, green color is variable. That depends upon how is the arrangement of the area. What is the distance of each and every elemental areas from the axis of, that is neutral axis. Okay, now, therefore, sigma dA y square, if it is more and more, if it is more and more, then I will tell you something now. Then it means the beam has got, the cross section has got an attitude of I don't care. See here, I don't care. Why? High value means beam is stronger. See, I don't care. That don't care feeling will come. Like for example, there is an elephant. You go and hit an elephant this way. First of all, the elephant may not feel it. It may not feel it. It may be eating something. It won't bother somebody is hitting. See, when so many people are there, it is used for people touching it. It will think somebody touched me. Or a boxer, a high, very strong, boxer. That is not wrestling, actually boxing. Very strong, world champion. Suppose he stands in front of you. You go and punch him. He will tell, okay, enjoy. You ask him, I want to punch you. Okay, punch. You should not get angry. No, okay. You won't get angry? No. Why? I don't care. See, I don't care. Okay, punch him. Anyway, he will just do this way. As if nothing has happened. Means it is called inertness. Inert. There's a word called inert. You know what is inert? Not responding. Or in Kannada, you can call it somari. I am telling for those, somari. In Hindi, it is called alsi. English, it is called lazy. Other language, I don't know. Lazy. You tell, see, first of all, remember, laziness, Kannadadalli, somari, alsi, that is bad. Someone will see here, he is very, very lazy. He is very lazy. See, that is a bad quality. But when it comes to deformation, it is good. It is not bad. See, laziness in daily life is bad, but laziness when you get strained, responding laziness is good. See, lazy people, what they will do, I don't care. Same way, when you apply the bending moment, see, bending moment, stress will come, slope will come, deformation will come. If the sigma dA y square is higher, stress will come lesser, deformation will come lesser, means it is lazy, inert. See, it is inert. You know what is inert? Not reacting. See, just like, see, you hit an elephant, it is not reacting. That shows its capacity. See, it will tell this is nothing for me. Your punch is nothing. Maybe elephant will tell, check your hand. Suppose you hit the elephant with the full powerful force, or a boxer, world champion boxer, you hit him with the full powerful force. He may tell you, hello buddy, check your finger, something is wrong. Oh, you will tell, yes, my finger is paining. Yes, what is this? I am hitting you. I don't care. See, I don't care. So, laziness in daily life is bad, but laziness against deformation stresses is good. See, when you apply high, when sigma dA y square is high, it will tell, I don't bother. See the feeling? I don't care. I will have lesser stress. I got capacity. Or when you apply loading here, it will tell, I will not deflect too much. I will not rotate too much. I will be almost, see, nothing. See here, if I take a beam this way, it is very, very strong. See, I will explain it later. Later, this example will come. See, it is very, very strong because it has got high moment of inertia. But if I turn the beam here, see, oh, see, very, very weak. If I turn here, low moment of inertia. But this way, very stronger. I will give an example later. So, the term sigma dA y square will show you some inert, or some word from my side, inertness. Inertness. Somebody will tell in English there is no word called inertness. My invention, inertness. Kannada, somaritana, RC, I don't know. Laziness. That inertness. Against what? Inertness against what? Flexure. Against flexure. See, bending stress is called flexure. This is also called flexure. See, the stress is coming due to bending moment. I told you flexure means bending. Actually, bending. Bending. So, inertness against, I can tell against what? Bending moment. That's why people decided it is better to use a word for that sigma dA y square. You use the word, see, inertness against bending, flexure, or inertness against what? No, don't care attitude. See, don't care. I don't care. It is very happy. Inertness against bending moment, or inertness against moment, or some inertia. Inertia. See, the word inertia, they decided to use the word inertia. Inertia means once again same thing. Inertness, inertia. See, this way. I don't care. Someone will come. Okay, no problem. Nothing happened to me. See, no, don't care attitude. So inertia. You know what inertia means? No response. It's a good actually. See, against bending, when it comes to deformation, inertia is good. Inertia against moment. Inertia against bending moment, or simply they use the word moment. That is why, okay, sufficient now. This much is sufficient. That is why, okay, now I told enough number of times now, you write, that is why sigma dA y square is called, technically called, what? It is technically called second moment of the area, about an axis, but structurally we call inertia against flexure, inertia laziness against bending moment, or laziness against bending they removed, laziness, inertness against moment, or inertia against moment, they reversed it, moment of inertia. It is not a moment unit. It is not a moment of force in distance, moment of inertia. Actually, I think correct word is inertia against moment. It is not a momentum. See, it is moment of inertia of cross section about an axis. An axis, in all these cases, it is about neutral axis, which passes to centroid. Now you know the meaning of moment of inertia, why it is called moment of inertia. Okay, now I will go for, I told you, I will first explain to you why it is called moment of inertia. I explained, sufficient. Now I also told you, I will give a feeling for you. Feeling, I will give it now. That feeling before I rub the board, I forgot one thing. right here. Therefore, in future, we will not write like this. We will not write like this. What we will write is in future. Therefore, in future, oh, I already crossed it. In future, I write here. Okay. In future, we will write sigma, that is bending stress developed at y from neutral axis due to bending moment for cross section, that is m equal to m divided by our most important I about neutral axis into y, and okay, this is over now, and we will write all this. We will not write this way for flexural deformation, right? Once again, we will write, say I should have written earlier, I about neutral axis. See, that I neutral axis is called, that EI is called flexural rigidity. One thing I forgot. Okay, sorry. One thing I forgot here. See, I'll tell now only. When you consider bending stress sigma, your I will give you how much it is laziness. How I don't care. It will tell you it's don't care attitude for stresses. Same way, this will tell you how stiff beam is. How stiff beam is. Stiff and rigid. See, as the I value increases, bending strength point of view, beam becomes stronger in resisting bending moment, and also beam becomes stiffer. See, I less, very, very weak. See, now see, I higher, very stiff. See now, very stiff and rigid. It gives you more stiff, increases, beam becomes more stiffer and rigid, which are all good. Therefore, I should tell one thing now. I forgot right last time, I write now. Therefore, one conclusion. See, you write all these, one conclusion. Then I'll go to example. Okay. I think I record a little more. One conclusion. Therefore, as moment of inertia I increases, it's not writing properly. Now see, I wrote moment of inertia. Okay, I write full. These are all statements, very important. As, I write fully, as moment of inertia of cross section about neutral axis, that is I neutral axis, increases, then bending stress is lesser, bending stress developed is lesser, comma, slope and deflection, that is flexural deformation is also lesser, that is very, 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 very good, or that is beam cross section is stronger in resisting bending moment, and stiffer and rigid rigid in resisting deformation. Deformation means that is again very, 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 very good. Very, very, very good. See, as I increases, stress becomes lesser, means beam is stronger. It no care, and slope and deflection lesser means stiffer and rigid, and vice versa. Vice versa, you write. As I decreases, bending stress will increase. Slope and deflection will also increase. Very, very bad. Or beam becomes weaker in resisting bending moment and less stiffer and less rigid in resisting deformation, means beam will undergo high deformation, therefore very, very bad. You write the statement. Okay, now I am going for something. I decided to record now only. Now I am going for feeling. See, so far you make a note here. So you write, so far he crystal clear made concept clear what is moment of inertia. Now that term feeling, or what I told, he told he can see, but can we really see? Can we really see like him? You write there. He told he can see moment of inertia when you look at a beam. Okay, he knows subject better. But can we see? I will try my level best for that one. For that one, what I will do is, see, I will go for a most important example. Okay, now where we have to find moment of inertia. We have to find moment of inertia about some axis, say AB. I won't come for neutral axis now, neutral axis later. Say AB, some random axis. Now, see, consider an area, right here, rectangular area. Any random, see, this width is something like, say, 200, and this thickness is 200 by 150. We want moment of inertia about an axis AB. It is, see here, simply axis AB. Imagine this distance is, perpendicular distance is something like 450 millimeter. All dimensions are in millimeter. See, we want to find moment of inertia of given rectangular area about AB axis. Okay, now do one thing, something you write now. There are two options are there. I'll put option 1. See, option 1, but actually not good. Option 1, that is pure basic. See, I will put the section here. Pure basic. See, this width is 200, this thickness is 150, little bigger. Okay, 150. Okay, somewhere here I write 150. Pure basic. Okay, now this is your axis AB. Distance from here to the axis is how much? 450. All dimensions are in millimeter. Okay. Now, what we will do is some statement I will give you. Consider elemental strip of thickness. See, our distance is y, so dy at y from axis AB. You should write, I will dictate now, see, no time. This elemental area is dA. See, dA is elemental area. Some statement I will give you, those who are serious should write it. You should not tell, he has not written. No, you are learning, I am teaching. You should follow what I tell. Consider elemental strip of thickness dy at y from AB, let dA be area of the elemental strip. Then write, area of elemental strip dA equal to 200 into dy. 200 into dy. Therefore, moment of inertia, see, moment of inertia of elemental strip, elemental area dA about AB, that is IAB equal to dA into y square. IAB, see, for elemental area dA is dA into y square. Therefore, moment of inertia, okay, red color, okay. Therefore, moment of inertia of entire rectangular area about AB, that is your IAB for the entire rectangle, is what? Integration of dA into y square. Now limit for y required. See, limit for y. See now correctly. Your rectangle starts from here, ends here. From here to here is 450. That is the lower limit. And from here to extreme fiber here is 450 plus 150 is 600. Is y equal to 450 to y equal to 600. Now 1 minute, I told you regarding limit, I will upload one more class in YouTube later, or equal to, see here, integration 450 to 600 of dA, where is dA? dA is 200 dy into y square, or equal to 200 into y square dy. When you integrate, it will become y cube by 3. That much you are knowing, so upper limit. I won't waste time. 600 cube by 3 minus 450 cube divided by 3. Your answer will come in millimeter power 4. This is millimeter power 4. This is by basic calculation. Okay, 1 minute. 200 into bracket 600 cube divided by 3 minus 450 cube divided by 3 divided by 10 to the power 6. 4162.5. It is 4162.5 10 to the power 6 millimeter power 4 is the answer. This is from base using basic concept. See, this is using basic concept. Now you should write something. Okay, now some note you are write. Okay, this over now. See, this I'll remove. 1 minute, I check the answer first. Parallax theorem. 1 minute. 200, 250 cube plus 200, 250 into bracket 450 plus 75 plus 8325. What is one? 200 into 150 cube divided by 12 plus 200 into 150 into bracket 450 plus 75 close square 8325. No, something wrong here. One niಮಿಷ here. Something wrong here. 1 minute. 600 cube. I think calculator problem. 600 cube minus 450 cube equal to divide by 3 into 200 is 832. Oh, see, it is answer. Again, calculator problem. 600 cube minus 450 cube divided by 3 into 200 is, it actually 8325 divided by 1 10 to the power 6. 8325. Okay, some calculation is wrong. I can make out, I will tell you why. It is 8325 into 10 to the power 6. Correct, huh? 8325. Okay, over. Sorry. Sometimes it happens. What to do? Now, do one thing. One note you have to write. One note I will tell you, you have to write now. What we have done is, we did by basic calculation. But that is not the way we will do in future. We will stop now. We are going to use a theorem called parallel access theorem. And right here, this parallel access theorem will be systematically and in detail with the crystal clear concept will be explained in the coming classes. For that matter, all the problems we have solved on centroid, we will go for moment of inertia. Everywhere you are using parallel access theorem. Now, why so early? Because I told I am going to give a feeling for you. If I have to give a feeling for you, or you should see moment of inertia, how inner mind, then this will not give correct idea. Parallel access theorem will give perfect idea. So therefore, I will use parallel access theorem. See now. Therefore, now let us find I about AB using parallel access theorem. You write here question mark. He will explain later. Okay, start. Write the area here. See, this is area, this is 200, this is 150. Your axis is here, AB. This distance is how much? 450. All are in millimeter. Now, according to by parallel access theorem, see, right here. By parallel access theorem, this I remove. By basic order, see right here. By parallel access theorem, 150. Okay, 150. By parallel access theorem, I about any axis, see AB, equal to IG plus A into one red color H square. You write here. This will be explained to you. Don't worry. I am now, but I require today only. What to do? Problem is what? To give you feeling of moment of inertia, I require parallel access theorem. You write there. He will explain later. Okay, now I won't waste time now. Equal to, see, IG means, right, moment of inertia about of the rectangle. See, moment of inertia of rectangle, here rectangle, about its own centroidal axis. And H is perpendicular distance from centroid of rectangle to required axis, that is AB axis. Therefore, if you use parallel axis theorem, your IAB equal to, see now, correct. Mark centroid. What I am telling is very important now, because I am going to give multiple examples now. come to centroid, its own G. You draw an axis, a centroidal axis, see, parallel to AB, parallel to required axis, that is important, required axis, that is AB. So what you do, parallel to AB, you consider a centroidal axis. I think everybody who is studying this subject, they know for rectangle, I above this axis, parallel side B into D cube by 12. You will be knowing it. It is 200 into 150 cube divided by 12. Because later, you write here, later we will prove for a rectangle, if this is B, if this is D, we will prove I about this axis is BD cube by 12. B is the parallel side, 200 into 150 cube by 12, plus area. What is the area? 250 into 200. 200 into 150 is the area into, from centroid to this axis, perpendicular square is 150 by 2, 150 by 2 plus another 450. Plus 450 whole square. See, from here to this axis, this perpendicular square, see, this is your H. H, that is 150 by 2 plus 450 square equal to, see, when I wrote wrong number there, how I came to know wrong? Because I applied parallel axis theorem and got different answer. Actually, I don't have to check now. 200 into 150 cube divided by 12 plus 200 into 150 into bracket 75 plus 450 close square is 8325. 8325. It is 8325 10 to the power 6 millimeter power 4, right? Oh, same answer as we got from basic. Now make a note. Now I am going to give you the feeling of moment of inertia. Right? Now he is going to give feeling of moment of inertia. When he is going to give feeling of moment of inertia, one example is taking where he will find I around 5 times. All the 5 times he will use parallel axis theorem, because parallel axis theorem will give you more concept. Your feeling will come when you use parallel axis theorem. Okay. So even though theorem is not done, right now you believe me. Okay. I'll make board ready. Now, question or example, actually not a question, details of example. Details of example, I will dictate here, then I will rub it out. See, right? They consider a rectangular area 400 by 60. You write there, 400 by 60. Horizontally 400, vertically 60. See here, one place I will write 400 by 60. Then we want to find moment of inertia about an axis AB. Where is AB? We will first case 1, you write case 1, AB is also, see AB throughout these examples, AB also is horizontal, that is parallel to 400. AB also is parallel to 400. A case 1, AB passes through centroid of the rectangle. Means correctly centroid here, see AB here. Case 2, AB is at bottom edge of the rectangle. Bottom edge of the rectangle, see here. Now I won't write here. 400 by 60 you write, no time to write 400 by 60. Case 3, AB is 100 mm below bottom edge of rectangle. Case 4, AB is further bottom, 250 mm below bottom edge of the rectangle. Case 5, AB is 500 mm below bottom edge of the rectangle. You should write the question, see otherwise it will not be clear. First you write the question. Okay, now, everywhere we will find I about AB, moment of inertia about AB, using parallax theorem. Just now I explained, I won't explain once again now because later it will come. Suppose anything is not clear, you see only answer. You see only answer. How it came, you study later. Once I complete parallax theorem, Ig plus A square. Okay, start. Here, I about AB. First, I about, see now. First, I about its own centroidal axis. 400 into 60 cube by 12 plus area 400 into 60 into 0 square. Why 0 square? Because centroid is here. See, the AB axis passes through centroid 0 square. Answer will come 7.2 10 to the power 6 millimeter power 4. That is Ig for the rectangle. Now, come here. I about AB. First, I about its own centroidal axis. 400 into 60 cube by 12 plus area into this distance square. See, area into, see here, this distance square. This is your H. Here, see, this is your H. Here, this is your H. Here, this is your H. Okay, now start fast. I about its own axis. 400 into 60 cube by 12, area 400 into 60 is the area into this H is exactly 60 by 2 square. First answer is 7.2, second is 21.6, total 28.8. Come to figure number 3. Once again same thing, Ig plus area into this distance square, that is 60 by 2 plus 100. 160, see this H is how much? I will tell you now. Here your H is 0, your H is 0, your H here equal to how much? 60 by 2 is 30. Here H is 60 by 2 plus 100 is 130. 130. Here your H is 60 by 2 plus 250 is 280. Here your H equal to 60 by 2 plus 500 is 530. Okay, sufficient. So here, everywhere, here Ig plus area into 130 square, I written correctly here, see, number is there. Ig A square, Ig A square, Ig A square. This should be clear. If not clear, study later. Now is the time for feeling. Observe something. All the five, see, now I will dictate something. I will dictate. What all I dictate or explain, if you are serious and really want to learn, you should write everything systematically. Otherwise, your problem. Okay. Therefore, first case, Ig itself is the answer. Second case, to Ig, extra 21.6 came. Third case, extra 405. See, no extra here, 0. 405. Next one extra 1881.6 extra. Next one extra 6741.6. Or if I take ratio of all these, divide throughout by 7.2, it will be 1. See, divide throughout by 7.2. 1 is to 28.8 by 7.2 is 4. This one by 7.2 is 57.333. This number by 7.2 is 262.333. That number by 7.2 is 937.333. Or if this moment of inertia is 1 unit, it jumped to 4 times. It further jumped to 57.333. What is this? Such a severe jump. Then it jumped, furthermore jump. See here, 262.333. Lastly, terrible jump, 937.333. So moment of inertia is increasing rapidly. Suppose you draw a curve, see, suppose as you slowly move away, how the curve will come, Ig, it will come this way, see, not linear. See, if linear is something like this, no linear, severe jump is there. No, that all you bother later. Or make a note, as the distance from neutral axis or centroid increases, moment of inertia will not linearly increase. It will rapidly increase. See here, 250 here, 500 here. Somebody will tell, so should come double. No. See, 262, 937, nearly 4 times. If you pay 100 rupees, you get something. If you give 250 rupees, something you will get. But if you give 500 rupees, he will give 4 times to you. Why? He will tell, sir, starting is, sir, 250 rupees, this much. But you give 500 rupees, he will give 4 times. Money is only double, but see, almost 4 times, ignoring 7.2, this number. Or, as the area is, see, I am dictating now. This all you are right. As the area, see, I told you, those who want to learn should write it. As the area is at more and more and more distance from axis considered, moment of inertia severely increases. Or this is called dispersion. How is the dispersion of area with respect to everything you are right? If you are serious, axis considered. Axis considered. Sometimes why don't you write, sir? No, if you want to learn, write it with respect to axis considered. See, there is a limit for everything considered. Or more and more away from the axis area, moment of inertia rapidly increases. So unbound increase. So that is moment of inertia. You should write everything. Increases means good news, not bad news. Oh, beam becomes more stronger, more stiffer, more rigid as the area is placed at further and further away from the axis. Therefore, when any part of the area is placed more and more and more away from the axis, away, far away, means it is stronger case. So that is called dispersion. So moment of inertia finally decides on dispersion of the area. More and more area is placed away from the axis, stronger. High moment of inertia means stronger, stiffer and rigid. So, and place area lesser distance, moment of inertia will be lesser. No good, bad. So therefore, you can see here now, as the distance increases, how rapidly moment of inertia increased. Okay, now this much is sufficient to understand. Now a slight feeling will come. And now I will give the feeling, more and more feeling for you. Okay, now I will go for some examples where some strength of materials formula is used. You believe me, at that time, you see only I. Other than I, you do not see anything. That's all. Okay, anything else to tell? So I told lastly, moment of inertia is mainly based on dispersion. More and more and more away from the axis, you place at far off distances, moment of inertia increases. Okay, I will give an example for you. Oh, no, not now, later. Later I will give. About army fighting a war. Bit later. Now, the most powerful example, and slowly feeling will come for you. 1 minute, I will show the feeling for you. I will dictate something, you write. For today's class, you consider a simply supported beam of span 10 meter, huge span. See, some will tell, sir, that much section is not sufficient. Don't bother about. We are not knowing about strength today. Example, deliberately I am giving a weak section. Simply support beam of span 10 meter. It is loaded by UDL of 30 kilonewton per meter over the entire span. For this beam, cross section, see, the cross section is case 1 rectangular of one side 100 mm and other side 300 mm. Everything you are right, 300 mm. Now, case 1 will go for two cases, further cases. Instead of case 1, I'll do one thing now. Okay, case 1, two subcases. See, two subcases. One dot. Okay, this is actually of case 1. You write here example 1. Okay, example 1. Example 1 you write here. Then write here two cases. Case 1 is shorter side horizontal, and case 2 is longer side horizontal. That means your case 1 is like this. See how much cross section I told? 100 by 300. This is case 1. Your case 2 is longer side horizontal, that is like this, 300 by 100. Okay. For both the cases, find maximum bending stress. That is called sigma maximum. And also maximum slope and maximum deflection. See, so many things has to still come in strength of materials. Formulas, if not clear, you don't bother. Okay, right here. Now, for the question, in the question given, for all the, see, after example 1, furthermore examples are there. For all the examples, you take Young's modulus of elasticity E as 200 10 to the power 3 MPa. MPa means Newton per mm square. Okay, that all will come later. This is the question. Okay, now, before you start, do one thing. Put the beam. This I am not removing. Subjected to UDL of 30 kN per meter. Make a note. We are asked to find maximum bending stress. See, sigma max. Maximum bending stress is M max divided by I into Y. I about neutral axis. I about into Y. And Y, which Y? Maximum Y. Extreme fiber. That all you will get in the bending stress chapter. Today you believe me. And write this formula. M maximum BM for this is WL square by 8. If this is not clear, leave it. WL square by 8 equal to W 30 into span 10 square by 8, 375 kilonewton meter is the maximum bending moment. And later write maximum slope is WL cube by 24 EI. Maximum deflection is 5 by 384 WL by I. E is 200 10 to the power 3. Okay, this is question. That's all now. See, this is where you will start understanding. Okay. First, example 1. Example 1 is example 1 case 1. Case 1 is cross section is like this. I told this is the cross section. How much width here? Width is 100. All dimensions in millimeter. I won't waste time. Overall depth is how much? 300. This is the neutral axis. From neutral axis to extreme fiber distance is, this is your Y maximum. Remember, this is your Y maximum either side. Y maximum there and Y max here. You write directly your Y max equal to 300 by 2. 300 by 2 equal to 150 millimeter. Because you make a note here, maximum, we make a note, maximum bending stress. See, I won't waste time again. Maximum bending stress will be at extreme fiber. And this is a BMD with sagging positive. So, for a sagging BM, top fiber, see, here you will get maximum compressive stress. You just ignore. Here you will get maximum tensile stress. You just write all these things. Don't bother. This all you worry later. You concentrate only on moment of inertia. That's all. Okay, start. Now, I can remove this one. Okay, this I can remove. This also I can remove. 375 should be still there. Therefore, what happens now is, see, one by one I will solve. For case 1, for our case 1, you should write maximum bending stress. See, if you are lazy and if you cannot write, what I can do? Sigma max equal to, what is formula? See, our basic formula is M by I equal to sigma by Y. Therefore, maximum stress equal to maximum M divided by I about neutral axis. Red color is important for you. Into Y maximum equal to, okay, now find I about neutral axis. I about neutral axis is, see, 100 into 300 cube by 12. That all you worry later, because you know it, 100 into 300 cube divided by 12. Is 225 10 to the power 6. 225 10 to the power 6 millimeter power 4. Therefore, your sigma maximum bending stress, you write at the top fiber it is maximum compressive stress, at the bottom fiber it is maximum tensile stress. Why? No idea. Equal to M maximum 375 kilonewton meter. This all I will tell you later, 10 to the power 6 y. I am converting to Newton millimeter. Divided by I, 220. These all you don't bother now. You see only I value, only I value. Into Y max, I told how much? 150. 150. So maximum bending stress is 375 divided by 225 into 150 is 250 Newton per mm square. Oh, heavy stress will come. 250 Newton per mm square. Okay, I'll make a note here. 250 came. Then I want theta maximum, deformation. Start. W, 30 kilonewton per meter, convert to Newton per millimeter. 30 into 10 to the power 3 by 10 to the power 3 into L power 4. 10,000 power 4 divided by E, divided by 24 divided by E is 210 to the power 3 divided by I is already known for you. See, your I is the more important term. Divided by 225, red color, 10 to the power 6. This will come 30 into 10,000, 10,000 power 3, WL cube, okay, 10,000. See, unit conversion all you don't bother. You see only I value, that's all. See only I value. 30 into 10,000, 30 into 10,000, I store the number 10,000 cube divided by 24. I require it repeatedly later, so I will store in store 1, store A, and store B I will make 5 by 384 into 30 into 10,000, 5 by 384 into 30 into 10,000 power 4. Okay, I can divide by E also. Divide by 200 10 to the power 3. I will store it in store B and shift store A, divide by 200 10 to the power 3, store A. Okay, it is store A divided by 225 10 to the power. Store A is correct. Shift store A is 62500 now. How? 30 into 10,000 cube divided by 24 divided by 200 10 to the power 3 is 2.5 10 to the power 3. 1 minute. Store A. Then store B, 5 by 384 into W is 30 into 10,000 power 4 divided by 200 10 to the power 3. Okay. Store B. Okay. Shift store A divided by 225 10 to the power 6. 0.111. What is this number? Something wrong. Shift store A. Hey, something wrong. 30 into 10,000 cube divided by 24 divided by 200 10 to the power 3. Store A. 5 by 384 into 30 into 10,000 power 4 divided by 200 10 to the power 3. Oh, something went wrong there. See, when I made power 4, something else came. 5 by 384 into 30 into 10,000 power 4 divided by 200 10 to the power 3 equal to. Still I got out. Store B divided by 225 10 to the power 6. 8, correct. Okay, now 86. The correct answer 86. Okay, 1 minute. That one is 30 into 10,000 cube divided by 24 divided by 200 exponential 3 equal to divided by shift store A is 1. Correct. Okay. Shift store A divided by 225 10 to the power 6. 0.02. This will come 0.027778 radians, or if you convert to degrees into 180 divided by shift pi, these all you don't bother. 1.5915 degrees. Okay, I'll make a note here. 1.5915 degrees. I'll just do one thing. I'll take a pause and calculate everything first of all. Before I go to the next part, I'll check the answer. And delta max equal to 5 by 384. W is 30 into 10 to the power 3 by 10 to the power 3 for conversion. Don't bother. Into 10,000 power 4 divided by E is 200 10 to the power 3. See, these all you never bother. Divided by I, 225 10 to the power 6. This will come. Shift store B divided by 225 10 to the power 6 is 86 too much. 8056 millimeter. Oh, 86 point. I'll check once again. 86.8056 millimeter. I'll do one thing now. I'll take a pause and check all the values. Instead of struggling in the class, that is better. Prepare the answer. It is much better. Because sometimes calculator gives problem. Okay, all are correct. So I noted the answer there. Stress will come how much? 250, 1.5915, 86.8056. Okay, correct. Now go for case 2. Case 2. I told case 2 is a rectangle. Cross section is this way. Actually very weak. See, this is 300. This is 100. That is case 2 is this way. I already told it. Longer side horizontal. 300, correct? Is the correct 300. Okay. Now, see, this is neutral axis. Neutral axis. Extreme fiber distances will be 50-50. If not clear, I can't explain anything. 100 by 2, 50-50. So your Y max will be 100 by 2 equal to 50 millimeter. Maximum, see, this is gone. Now same way you write here, sigma max equal to, instead of I equal to, how much I know? 300 into 100 cube divided by 12. will come, I think 25 I got. 300 into 100 cube. 100 cube divided by 12. See, 25, correct. 25, 10 to the power 6. So now sigma max equal to, instead of 225 here, everywhere you are right 25. See, now moment of inertia is 25. 25, this also 25, this also 25, and y max is not 150, y max is 50. The stress will come 750 Newton per mm square. Oh, too much. This slope will come, I noted down there, 0.25 radians. 0.25 radians. That is 14.323 degrees. Horrible. And deflection will come now 781.25 millimeter. Horrible. Or, okay, now lastly, summary I will give you. This is your case 1, case 2. Okay, now something little more is there, concept. See, complete feeling will come when I finish all the examples now. Okay, this is over now. Any mistakes? People are there, search mistakes. 100, I changed everything. Everything I changed, I think. 300, 100 cube by 12, 25, 25, 25, 25, everything changed. Okay, I noted the answer there. Now, lastly, I will give example for you. Okay, I will give final summary. At that time, I will give complete history for you. Then that is where you will get that feeling. Okay, I won't waste time now. This is 375 kilonewton meter. See, something you can see there, that is my preparation. Now, example 1 over example 2. Once again, go back to rectangular section. A rectangular section of 100 by 300. 100 by 300. The 100 is horizontal. Horizontal. That is, cross section is like this. Once again, 100 here. This is where you will learn the concept. This is 300. This is the axis. Okay. Now, distance not required, 50-50. Now, just now we got sigma max. How much answer? 250 Newton per mm square. 250 Newton per mm square. And theta max, maximum slope, 1.5915 degrees. And deflection maximum, we got 86.8056 millimeter. Okay, now compare this result, compare this with other case of rectangular cross section of this way, 300 by 100. 300 by 100. This way. For which you got sigma max. No, example 2 later. Okay. Once again, go back to rectangle section. Sigma max equal to, how much you got? 750 Newton per mm square. Theta max, slope maximum, we got 14.323 degrees. That deflection maximum, we got 781.25 millimeter. Actually, somebody will run out of building, nearly 1 meter. Beam will so weak. Okay, now go for some concept. Using a scale. Okay, I will go this one, then I will go to the last part. See, our first example is longer. See, this way, 100 by 300. Beam is stronger. See, because moment for this one, I want a moment of inertia. See, for this one, your I is about neutral axis. How much under I? I forgot it. I will calculate what is there. 100 into 300 cube divided by 12. 225. I is 225 10 to the power 6 millimeter power 4. Here your I is 25 10 to the power 6 millimeter power 4, that is 225 divided by 25 is 9, or this beam has moment of inertia 9 times of that beam, or that beam has moment of inertia 1/9 of this one. I told when I is more, beam is stronger. See here, when the longer side is vertical, shorter horizontal, see, beam is stronger. See, you cannot bend so easily. So stress will come lesser. How much? You should write everything. Only 250. And slope, very small slope. How much? Almost 1.5 degrees. Deflection 86. Actually, little more actually. Okay, some deflection is there. Okay, but when you turn the beam this way, when you made longer side horizontal and short side vertical, or see, this beam is, I will show you the beam. This beam is something like this. How I have to show it? Okay. This is the beam. This beam is see, very, very weaker. This is stronger. See, high moment of inertia. This is weaker, less moment of inertia. See here, if I take a scale, if I bend this way, depth is more, it is stronger. See, stress is only 250, slope is 1.6 degrees, deflection 86. Actually, 86 is too much. But when I turn the beam this way, see, horrible, gone case, heavy stress. 250 jump to 750, high stress, high slope and high deflection. Okay. Or tell the reason for this one. See here. Reason. In the first case, see, when your longer side is vertical, see, more and more area is dispersed away from the axis. When you take the shorter side vertical, then area is somewhere near the axis. See here, area is much away, dispersed much away, therefore stronger, dispersed nearby, therefore weaker. But the critical example, the real feeling you will get when I go to next example. Now, last example, see, now, new example, actually number you don't bother. One new beautiful example, no, one beautiful example, you write here, one beautiful example when you will get that feeling for moment of inertia, What you do is, first consider, see, that longer side vertical, leave it, that is not required. Nobody will place the beam like that. You once again go back, consider rectangular section, 100 by 300, 100 mm by 300 mm. Okay. How beam is like this, see, beam is like this, 300 depth. Width you cannot see, okay, this way, and this depth is 300. Then at this point and this point, sigma max, you got how much? 250 Newton per mm square at center, Y center, there and here both, and beam will deflect like this. So this maximum deflection is, how much you got? 86 point delta max is important. delta max. Okay, only delta max sufficient. 86.8056 millimeter, and this rotation theta max we already got very small, out of scale, 1.5915 degrees. Now what you do is you replace this beam by an I section of same area, very important, same area. Why same area? Because when you are comparing, area should be same. I'll give an example for you. Suppose you buy 1 ton of steel, cost may be around 70,000 rupees in India, I don't know. Whereas buy 5 grams of gold, or just 1 gram of gold in India, cost is around 7,000 rupees. So you cannot tell steel is costlier. See, steel you have paid 70,000 rupees. Gram is only 7,000. No, what you do, if you want to compare the cost, if you buy 1 ton of steel, go to a jewelry shop and ask him, I want 1 ton of gold. Most probably he will faint. If you tell jewelry shop person, I want to buy 1 ton of gold, he will almost faint. So then it will come how much? 1 ton of gold will come. See, if you want to compare the cost, both you buy same. 70,000 is per gram, 7,000 per gram into what? 1,000 per kilogram into 7,000. How much? 1,000 by tons. Divided by exponential 7. It will cost you 700 crore rupees. 1 ton of steel will cost you 70,000 rupees. 1 ton of gold will cost you 700 crore rupees. So what you do is same area, but right here, same area, but different dispersion. Okay, I will tell you, say I section. See, I prepared I section there. This is actually in steel, you get it, steel structures. This way I section. Now is the time for understanding. See, I section like this. Divide into parts, no problem. Divide like this. Okay. Let the width of I section be, how much I taken? 250 mm. 250. I have taken thickness of 40 mm. This thickness of 40 mm. See, this cross section is 1 minute now. I want cross section here. Okay, 1 minute here. I want cross section. 100 by 300. See, axis. Okay, now this is the cross section. This depth I will make 500. 500. This thickness I will make, how much I took? 20 mm. 20 mm. 20, all in millimeters. So overall depth of I section is 580 millimeter. This is the axis, neutral axis. See, neutral axis. This distance and this distance will be 580 by 2, 250 plus 290, 290. 290 and 290. Now, those who got doubt, check the answer. This I section area is same as this out of scale. I should have taken a little bigger here. See, this cross section little bigger. Okay, little bigger I should take. Okay, I'll put somewhere here. Cross section. How much? 100 by 300. Okay. Leave it. Okay, 100 by 300. This question. Overall 300. This is 250, 250, half. So 150, 150. This part. 1 minute, I'll go later. Okay, leave it. Okay, now, if you find I about neutral axis, you don't find now I about neutral axis. It will come, I already calculated, 1669, 10 to the power 6, millimeter power 4. Okay, I will do one thing now. This beam I will remove to make it more clear. 1 minute, before that one, if somebody got doubt whether same area is there or not there, see the area here, 250 into 40 into 2 plus 20 into 500, area is 30,000. See, the total area is 30,000. 30,000 mm square. This here also. Okay, I remove this one, not required. See, here. Earlier, cross section is this way. See, 100 by 300. 100 by 300. 100 by 300. Axis here. Sometimes when I record too much, when I feel tired, it happens always. Okay, no problem. This is 150, 150. 150, 150. This is, see, 290, 290. Your I will come 169, 1669, 10 to the power 6. Now do one thing. You calculate once again sigma max and theta max and delta max. You calculate. I will tell you. Sigma max. Bending moment M, 375 10 to the power 6 divided by this I into y equal to 290. Sigma max will come 65.159. It will come. So you believe me, because our class is not sigma max now, maximum stress. Theta max will come very small, 0.215 degrees. And deflection will come 11.7024 millimeter. And remember, this I is how much? 225 10 to the power 6 millimeter power 4. Whereas this I is 1669 10 to the power 6. So huge increase. Maintaining the same area, but arranging as the I section, we got a very huge I. So now see here your sigma max, how much you got? Sigma max you got 250 Newton per mm square. See, these values all you take from me, don't bother. Theta max you got in degrees. Theta max is 1.5915 degrees and deflection maximum is 86.8056 millimeter. Now write what I dictate. When you replace this I section by replace this rectangle section by an I section with what? So that area is same. Area same means cost is same. How much money you have to pay for this beam in material, same amount of money you have to pay for this beam also. Cost depends upon area, not upon dispersion. Okay, here I is 225, I is 1669. You can write here severe jump, right here. Severe jump. And these all drastic drop. Here what happened? Drastic drop. Both are good. Why both are good? Moment of inertia increasing is good. Stresses and slope and deflection decreasing is good. So very, very good. Now that feeling for this one. See, here your area, what I tell you to write. In the rectangle section, area is dispersed for a length of 150 mm. Equal dispersion. See, some area everywhere. If you take a strip by strip here, see, area is same. But in I section, huge area is at the outer fiber. See, it is shifted more and more away from axis. So here dispersion is more. Where bending stress is more, or where you get more moment of inertia, that way we provided area. That's why in steel structures always I section is used instead of rectangle section. You cannot see rectangle section in steel beam. Every construction steel, you can see I section. See, you can see like this when you go to steel structures. See? This way you can see beams. Okay, now this much over. Now I will tell you something very, very important, closing part. So here area is dispersed near to the axis. Here it is far off. Second is here near the axis and away from the axis, area is same. See, if I take a strip here or strip here or strip here, same. But here, away from the axis, if I take a strip here, area is more. If I take a strip here, area is lesser. Near the axis, lesser area, far off, higher area, that is the most effective. Means I told you moment of inertia is always more when area is dispersed far and far away from axis. Okay, now I will give a beautiful example for you to get the final feeling. Final feeling, I will give an example. You imagine a country, some country, see, not your country, some country. This is easy to understand. See. Some country, see, this is sea. Sea is there. Here also sea is there. Sea is there. This is the capital. This is the capital of the country. I should get dry. This is a very powerful example to understand. See, this is sea, water. See, here also sea. Huge long distance is there. This also sea. Here, see. Here there is another country. Other country. Other country is there. Here also other country is there. This is your country capital. See, this is your capital of your country. Now imagine this distance is very huge. Say 600 kilometer. Okay. Now army. This country has got army. Army of say 1 lakh people. 1 lakh soldiers. 1 lakh soldiers are there in the army. How to arrange the army? Imagine suddenly from this country and also from this country war declared. War declared. War declared. War declared. War declared. Or they invaded. War declared. Your 1 lakh soldiers, how you provide? Do you provide, see 1 lakh divide into 10 battalions or maybe not 10, okay, 10 battalions. Provide each battalion, how much? 10,000. 10,000 people here. 10,000 people here. 10,000 people here. 10,000 people here. Another 10,000 near here. Another 10,000 soldiers here. Another 10,000 soldiers here. Another 10,000 soldiers here. Another 10,000 soldiers here. Lastly, 10,000 soldiers here. That is your rectangular section. See here. Everywhere area pattern is same. No, this is not effective. If you want to win the war or get a good result, what you do is where trouble is there, trouble is here. See, this is the danger spot. Danger spot. Danger spot. What you do? Do not give that way. This is wrong. You employ high here of 1 lakh, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Both side war. 1 lakh people, you arrange 40,000 here. 40,000 here. And remaining 20,000 you spread here. See, remaining 20,000 you spread because by internal security. Remaining 20,000 you spread here. Let the major part be near the border. See here. More and more away. More and more away. Border. Employ more soldiers in the border. Say 40,000 there, 40,000 here. Remaining 20,000 you disperse somewhere here in between. See here. Disperse in between for internal security. Or maybe who knows. Nobody is coming from sea. But occasionally somebody may come from sea. See, but that will not be as severe as the land fighting. So if someone comes by sea here, you can fight them. So therefore, arrange 40,000 here. This is wrong. This is better. See here. Everywhere same area. Same pattern of area. Here, where trouble is more, more area, here less R. Where area is more useful, I told you, area is more useful and more contribution for moment of inertia if it is far and far away. So far and far away, more area, here lesser. See here, far and far away, near border, more soldiers, near capital, around here, less soldiers. I think sufficient. So I think by this time, when you see a beam, see, now, if you see a rectangular beam here and a rectangular beam here, suddenly to your mind will come, oh, see, dispersion smaller, dispersion higher moment of inertia. Or if you see an I section, see here, a feeling should come to you. Oh, outer fiber, more area, therefore good. So as I told you, all those who go through everything in this class, they will thoroughly understand. If somebody is not interested, if he is not going through, what I can do? Okay, now I will conclude it now. Already too late now. I have taken some 3-4 days time because of other commitments were there for me, and this is a long class. Recording took 2-3 days. So I will upload the class now, and from next class onwards, lecture 42 onwards, I will once again go back to moment of inertia, where this story all I will not tell. I will start as usual. Okay, hope by this time you really understood the real concept of moment of inertia and that feeling is coming. As you study more and more, get grip and understand, your concept will start developing, and finally one fine day you can come very nearly equal, okay, to me only. All the best.